Anderson. Hello, everyone. I know we're just in time at 4 p.m. and I'm going to start my presentation. It's a final stretch, almost final stretch, right? So the name of the talk, what does recomposition mean to your app? How many of you heard about Jetpack Compose? Oh, some people didn't? Okay. I would be surprised if you didn't. And how many of you use Jetpack Compose on a daily basis or like have tried working with it a lot? All right. Do you know what's happening behind the curtains of like Jetpack Compose world? All right, that's good to know. Then it means this talk will be really relevant to you because in this talk, as much as we want to discuss about the recomposition, we also going to touch base on the ideas of what's happening behind the curtains exactly in the Jetpack Compose. You know, what are some gotchas you have to keep in mind? And in order to get to that point, you really have to unveil entire curtain, see what's happening, sneak peek into that, know that kind of little bit of theory, I would say, and so then you can use that knowledge later when you're going to be building your composable functions. And so I am Aida Issayeva, I'm Google Developer Expert for Android, Senior Engineer at Twitter, blah, 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 and all these titles that you can think of them is me, right? And so in today's agenda, what we're going to be talking, again, briefly going to mention about the Jetpack Compose paradigm. Then we're going to go into more details like of the foundation of the Jetpack Compose, and then discuss what is the recomposition and what it means like inside that foundation, and then talk about smart recomposition, right? And why is it called smart? And also use some of the tools to detect and debug this recomposition, along with some practical tips. All right, so historically, Android view system is represented as a tree of UI widgets, right? Where in order to update one of the UI widgets, you would need to go through that tree, find that relevant node, that UI widget, pass the new argument via getters and setters of that UI widget, and then update that internal state inside that UI widget, right? But that approach was prone to errors. Why? Because by the time you reach that node, that node could have been removed, and and the update would not come through, and instead you would get this null pointer exceptions, right? Jetpack Compose, on the other hand, is a declarative UI framework. You're going to hear that a lot, declarative, right? It means UI widgets do not hold that state inside. There's no state inside that you can update the value in. The only way to update some sort of a state inside this UI widget is by passing new arguments to the function itself, to the composable function UI widgets, right? And so Jetpack Compose built this kind of machinery to detect those new arguments, right? To understand what parts, what composable functions need to be updated and essentially need to be recomposed. And so how does this machinery work? Let me give you an overview. On top, on the high level here, we have Android operating system. Android operating system, right, communicates back and forth with the state snapshot system. Everything below that state snapshot system is basically a Jetpack Compose world. In Android OS, it's an Android platform, our Android platform. And so state snapshot system has observers, right, that are subscribed to the Android OS, and then therefore all these user interactions and so on awake the state snapshot system to notify the lower levels about the updates in the state, and hence the name state snapshot system. And all of those state changes, are passed down to the kind of a composition layer, and where Composer specifically, Composer compares the values in a slot table. Slot table is a sort of a in-memory representation, like in-memory cached array that holds the latest state information. Like it's known about the latest state of the screen. So it holds that information there. The new set of updates come from the state snapshot system, Composer compares that new state of information with the current state in the SlotTable. Once it notices there are changes there, what it does is it produces a change list specifically. And once the change list is produced, Composer again updates the SlotTable with the new changes, and then Applier comes into play that generates the UI node tree, and applies everything in the batch in the UI node tree that gets reattached to the Android OS, right? So this is it in a nutshell. We're gonna deep dive into the foundation to get better understanding of how that diagram works in Recomposition. So when we talk about composition, right, we have to understand that UI widgets go through 3 stages, right? 3 phases. The first phase being composition phase that answers the question, what UI to show? What it does is it calls the composable functions and creates a description of the UI, right? The next phase is a layout phase that answers the question, where to place UI. It measures and places all child nodes in a single pass. And that's where the modifier functions start coming into play. And the last phase is a drawing. It answers the question how it renders, right? So it draws the elements to the screen. Again, some of the modifier functions like background colors come into play in this phase. So order is always preserved. However, some of the phases may be skipped as well. And within these phases, Jetpack Compose has its own layers, where every layer is responsible for a specific part, right? So runtime and compiler layer, one way also to think about these layers as a sort of a separate modules, right? So you have to think about them as separate libraries, depend on each other, like runtime and compiler, right? They're like heart of the Jetpack Compose. They are platform agnostic, right? And they run that declarative machinery in place. While UI layer is Android platform specific, meaning if you want it, you can use that declarative machinery, like you can use runtime and compiler in, let's say, web, iOS, or other platforms, as long as you provide your own UI layer. So that's how you can actually modify and use Jetpack Compose in other platforms. Now, since we talk about Jetpack Compose, we have a UI layer that is the essential communicator between Android OS and the Compose world. It is aware about the Android lifecycle, context, accessibility, and so on. And because UI layer is an integration layer between Android and the Compose, it is also responsible for executing all of those composable functions. And it's done via set content lambda function that you add inside your, let's say, in this example, main activity. And on the other hand, right, this function is responsible for passing down all the platform-specific information like context, keyboard state, save state instance, and so on, all the way down to Compose runtime as a composition local. After the set content is called and relevant platform information is passed down to the runtime, Compose phases begin the play. And that's where the composition phase starts. And runtime is a vital component of the Jetpack Compose that contains all the logic and the execution. And within runtime, there are 3 important classes for us to keep in mind when it comes to recomposition. The first one is a composition class that has SlotTable, Composer, and change list. Those, I'm going to talk about those in a bit more in details. And so composition accepts parameters like Recomposer and Applier. Recomposer has the state snapshot system in a place that was talking to the Android OS earlier, and it also contains list of compositions. Why list of compositions? Because, like, let's say if you have a half Android, like regular Android app, you're introducing a Jetpack Compose, you call set content not only like in one activity, you may call in other activities, right? Or like in other views. And that way you're gonna create that compositions gonna get created, and you may end up adding those compositions into the list. So Recomposer has information about all of those compositions. And the last one is Applier. It's another class that is important and basically responsible for the last two phases, like layout and drawing, right? So let's take a look at the Recomposer and what's its job upon composition phase. When we think about Recomposer, what we have to do is to think about as a scheduler that is responsible like for triggering, awakening the composition phase, and passing down the updates to the list of compositions. And because Recomposer contains the state snapshot system that observes the OS changes, in the UI layer, we also have a window Recomposer class that initializes lifecycle aware Recomposer. And initialization happens in Android's view extension function here. And because it's Android's view, we can identify and locate the owner, the lifecycle owner of the view, and attach the lifecycle observer. Notice here in this snippet, upon onCreate, we're calling the function run recompose and apply changes, right? And this function registers an observer for the change propagation. When the change happens, the observer awakes, adds all the changes to the snapshot system that ends up passing down the changes to the composers, and so that composers can record what parts of the composition need to be updated. In other words, this observer basically is a first step for triggering automatic recomposition when the state changes. So what does state snapshot system do exactly? In the basic terms, it captures the state results at a specific read moment. Under the hood, Jetpack compiler wraps all the composable functions and declarations with expressions to automatically track that snapshot read state within the bodies. And that's how this the snapshot state is observed. The goal is that every time the composable state read varies, the runtime can invalidate the recomposer scope, so it can execute it again upon next recomposition. To visualize the snapshot system, let's create a function state snapshot system, right? That contains two states, name and the state is important. The state name is a type of string, and then state is important is a type of Boolean, right? And we also have a column with a checkbox and text. And you can assume that in the column where we have checkbox and text, user checks on the checkbox and then unchecks the checkbox, and that way Recomposer observer awakes, because it noticed the user interaction, and the state reading happens at this time. And when the state reading happens, because we changed the value of the checkbox from the false to true, we checked, and then we checked back again, the state snapshot system spits out three kind of states, right? Two of them related to the is important because we checked twice, and one is for the name, which has not changed, but however, the read happened at that time. Sorry. And then all the state results, right, that we have generated are passed down to the list of compositions. And in composition, composition is basically a process of executing these composable functions. I think it's also important to keep in mind there are initial composition that happens whenever you just create the composition from the scratch. There are no changes yet. The only changes that are applicable are the changes related to the creation of the screen in our examples. And so upon initial composition, the composition stores all the relevant information on the SlotTable, right? So SlotTable contains the latest state there. And upon recomposition, which means upon updates, right, to the state, all those changes get applied to the slot table and the UI node tree. And so in composition, we have three important elements: composer, slot table, and change list. What is a composer? Think of it as a manager that knows when to read, when to write to slot table, how to produce this change list, and when to produce this change list. Composer itself is an interface that helps Compose compiler, talk to runtime. Slot table is a in-memory flattened array that gets filled with information and contains the latest current state of the composition. It not only contains the UI widget functions, it also contains relevant information about that, like location of the function, parameters, sources, event handlers, and so on. So SlotTable basically contains everything there. And we also have a change list. Change list is a list generated by the composer based on the new state results and the current state information in the slot table. All right, so now let's pause on theory and use a simple composable function as an example to show how compose phases, with a slot table and the composer work together. And I'm going to use a simple composable function called card that has a column and text with a button inside. Because slot table is a representation of the current state, let's take a look how it gets filled upon initial composition, right? So first, composer creates a sort of a flattened array, right, with empty slots. And that array is a named slot table, but in the code it's named slot table in source code, but it's essentially a flattened array, like gap buffer. So then we have a function card, right, that this function will be called like within our app, could be inside set content directly, or could be somewhere in other composable functions. So runtime creates a group for the function card with some key. In this example, I'm using arbitrary number like 1 to 3 key, but that key is generated by runtime. So why group? Group is runtime's internal concept that represents a group of nodes, group of nodes that get created together, which means they enter the composition together, they leave the composition together, and move within the composition together, right? And so that brown line, it represents the scope of this group exactly, where it ends and starts. Next up, we have a column inside our function. And the column is a layout composable, which means we can pass other composable functions to it, meaning because it can contain other UI widgets, runtime assigns a group to it as well with a key. Again, in this example, I'm using 456, and it's represented as a group with its scope. Next is a text with a value compose. Because text technically does not accept another content, composable functions, it still takes up slot in a slot table because it contains a value that is relevant right now for this specific screen, and that way it has a slot with a value in it. Next up, button. Again, the same rule applies because button is a layout composable, therefore a group created by the runtime for it with the key, assigned key. Next one is an interesting one. Event handlers, like on-click listener, right? They are not composable functions. They are regular functions. However, they have slot and the slot table. Why? Because it's still relevant information to the state. And the last one is text, right? Another text, but it's inside the button with the value click me. So once we generated this slot table, we filled with this all the information, right, from our functions. It's important to keep in mind that slot table only records changes, of the latest state. It does not really display those changes yet. The composer, reads that slot table, one slot after another slot. Then it compares the new values, new information with the current information in the slot table, in the slot, right? And if that new information and the current information in the slot differs, what it does is it produces a change. And the change is a deferred action waiting to be executed. Once this change is produced, that change gets added to the list of changes. And after the composer completes this loop of going slot after slot, and the change list contains all the applicable changes, only then all of those changes will start executing. So all of those deferred actions will start executing. Meaning, writer will write back in the slot table, update the slot table, and meanwhile, applier will apply all the changes in a batch to the UI tree. And so, applier, another term, what it does is it's responsible for measuring, layout and drawing the UI widgets. And once applier begins its work, the layout phase starts. Because applier is an interface, inside the runtime, UI layer contains an implementation of it. It's called UI layer. However, again, if you provide your own UI layer, you may want to provide your own UI applier, your applier implementation. Right? It could be in web, it could be elements, right? Like elements applier or stuff like that, as an example. And in layout phase, there's another in-memory data structure come into play. It's called stack of UI nodes. And there are 4 distinct steps in the layout phase. The first one is adding child nodes bottom up to the root node, right? And the second one is passing down all the constraints from the root node, constraints like padding, right? All the information that comes from the root all the way down to child node, so we can measure those child nodes. And once we measure the child nodes, that measured information gets passed up again to the root node, so we can define the size of the root node, right? And once we identify the size of the root node, we can finally place all of those nodes on the screen. And after we place the nodes, the third phase begins, which is a drawing, where another modifier functions like background, text colors, and so on get executed. And once drawing phase complete, that change list that was produced by the composer gets cleared out. And so the final result will look like this. We have a text with a button, and inside the button we have another text, click me, right? So what is recomposition? Now we're going to our talk. In dictionary, recomposition means the action of forming something again. In Jetpack Compose, recomposition means the action of executing the function again, right? If in classic view-based system, in order to update an information inside our widget, we would call a set function, right, on the widget that would update an internal state. In Compose, we call the function again with a new input, with a new parameter. And doing so causes the function to be recomposed. And the UI widgets emitted by this function, right, are redrawn again with the new data, which means recomposition goes through the same compose phases all over again. However, Compose framework can identify what components that changed thanks to the composer, SlotTable, and change list, right? And that's why recomposition is I usually call it a recalculation of all the changes necessary for the composition state in our SlotTable and the materialized tree that can be updated via applier, and scheduling all of those changes. Worth noting that recomposition is optimistic and it will schedule changes, but it does not guarantee that you will see the changes right away, right? It does not guarantee that the changes will reach the last stage, that the last phase of drawing. If, for reason, if the new recomposition comes in while the current one's still in progress, the current one will get canceled and the new one begins from the very beginning. So that's something to keep in mind. Like let's say if something user frequently clicking on a button on the screen, right? And then the first click might get canceled because we have the next one coming in that causes recomposition. And so to give you an example about recomposition in the SlotTable, let's do the example one where I can introduce a counter variable, right, which is a state of type integer, and this state is read inside the inner text, click me at counter, right? So that's where this state is read. Now let's say user clicks on the button and our state gets incremented. Because event handlers, like buttons on click, are not composable functions, they're just regular functions. When the click handler is invoked by the framework, it is done outside of the recompose scope, so nothing inside the SlotTable changes, doesn't get updated. However, because we incremented the counter state, right, we can see the slot for the state is updated with a new value. We incremented to 1, so we have a new value integer there, as well as the text click me that is reading the counter did get updated as well. Now, example number 2. What if we're gonna read this counter not inside the inner button, but rather inside the outer text and perform the same action of clicking on the button to increment the counter? What happens here, we see, so state is updated. We also see the column 789, which represents the group 789, which represents a column, is updated as well too. And when it's updated, all the child components, all the child functions inside the column are updated as well, but not the inner text, because inner text has its own nearest recomposer scope, which is a group 101, and it is a button. So it always, whenever the recomposition happens, it always searches for the nearest scope and then updates that nearest scope as well as the children inside that nearest scope. And so recomposition goes through the same steps of updating SlotTable, right, as you saw an example, then generating that change list, then updating the node tree, measuring, layout, placing, drawing the UI, and attaching the newly generated tree to the view, which is potentially expensive, when we think of in terms of time, computing power, battery usage, and so on. And so to mitigate this cost, Jetpack Compose intelligently chooses what parts need to be updated at any given time. And it's possible via smart recomposition. If regular recomposition is responsible for updating composable functions, smart recomposition is responsible for skipping the updates. And the way how smart recomposition decides to skip recomposition is by making sure that inputs, the parameters of the composable function, are stable, right? So you want to make sure the inputs of the functions are stable. And so to detect this stability between runtime and compiler, runtime has a defined set of rules to help compiler to detect a smart recomposition. What are those rules? The rule number 1 is making sure that a result of calls to equal function for 2 instances will always be the same for the same 2 instances. Rule number 2, all public properties have to be stable as well. And rule number 3, whenever the public property changes, the composition is always notified, means the recomposition will happen. Also, speaking of property types, string and primitive types like integer, boolean, float, and so on, they follow the contract of stability because they're immutable by default. Also, if you annotate your property with the @stable annotation, it technically conforms the rules of stability as well. However, it's important to keep in mind that Jetpack Compose, it's still in active development, meaning compiler will have more support types added later, right, during the development. So be very cautious to add these annotations manually everywhere that you think. In the real world, however, we barely use just the primitive types. Oftentimes we use custom data types. So what happens when we use custom data types? How does runtime find out about the custom data types, and how does it know whether that custom data type is stable? It is possible via special algorithm from the runtime called Inferring Class Stability algorithm. So what does that algorithm do? It basically visits each eligible class, right? Then annotates with the stability inferred that each eligible class, and that way it helps compiler to determine what functions exactly recompose. So I mentioned about the eligible classes, which means there are some ineligible classes. What are those classes? Enums, annotations, inlines, companion objects, they are ineligible. So including the interfaces, right? Meaning, for example, collections, right? They're always gonna be annotated unstable in Jetpack Compose. Why? Because the implementation of the interfaces could be, it could be mutable list, or it could be just a regular list. There's no guarantee. There's no guarantee for runtime to detect the change in the interfaces. That's why it's still considered unstable. Okay, so we've done with the theory of how things should work. However, in practice, because a lot of things are still in development, meaning some of the things can break and not work as expected. And so as developers, it's a good practice to arm ourselves with some tools that will help us to understand the recomposition better, learn about recomposition more, and catch some of the bugs if needed. So the first tool that is available to learn more about recomposition is Compose Compiler Metrics, right? This tool gives you like full analysis of all the composable functions that you have in your app. It kind of spits out a JSON file with the top level metrics, including information about restartable composables, skippable composables, and so on. And what's interesting in this example that I have, you see we have a restartable composables 76 and then skippable composables 64. Now, if we do simple math, what it means is somewhere in the app, 12 composable functions, they do get restarted all the time, but it's not possible to skip them, which means if for some reason if for some reason the input is not changed in that composable function, the composable function ends up being recomposed again. Unnecessary work is happening. So that helps us to identify what exactly happening. Also, my colleague, Chris Baines, wrote a great article about Compose Compiler Metrics. I added in a list as well in the resources, so you can check it out, how to use the Compose Compiler Metrics. And the QR code is for the me about the compiler, how to follow and add it to your Gradle. So although this Compose Compiler Metrics gives you full analysis, right, it can tell you exactly where there's like phishing composable function is happening, right, with some details. There's one gotcha. As a developer, right, you have to run this analysis on the release build. It could be good, right, like if you're building app. However, when you build a feature, you want to see whether your build composable function works well or not ahead of time, instead of building that release build all the time. So that might not be as convenient, kicking off the release build all the time. Next tool is a Recompose Highlighter. It's a courtesy of Google Play team. This Recompose Highlighter is basically a modifier function. And what it does is it's a visually appealing modifier function that tells you, that shows colors for each recomposition count. And let's say if you have a lot of recomposition happening, the more closer that color is to the red, it means the more recomposition is happening, right? So the higher number of recompositions. However, I noticed one thing: if you have a nested functions, or like you're calling some of the functions inside another function, and you're trying to see whether that composable function is being recomposed, it is difficult to separate what function is exactly recomposed with this color highlighter. Also, manually adding this modifier function to each of your composable functions could be labor consuming. Right? Oh, well, there you go. So this is how it's going to look like. Basically, it will tell you what the blue ones means it was recomposed only once, the green ones means it recomposed twice, the yellow ones 3, and if you go closer to red, means it was recomposed more than 5 times, right? So that's where it's really good. I've also added the QR code for a snippet, code snippet that you can copy and use it. All right, and the next one. The next tool. Now, if you prefer to know exactly the number of recompositions, like along with the name of the composable functions, the natural step is obviously to create another modifier function just to log the recompositions. So I've actually modified the Recompose Highlighter and created a modifier function for logging, because to know exactly what composable function, what name is actually, what composable function gets recomposed and how many times it does get recomposed within like certain timestamp, like let's say within 300 milliseconds or 3000 milliseconds, right? Obviously, because logging is so easy to add and it's easy, understandable for all of us, right? It has some drawbacks, like it creates too much noise in the log cat, right? And it also could be a labor consuming, means you have to add that modifier function to each of your composable functions if you want to go deep dive into understanding what exactly happening, like how many recompositions happen. And the last tool is the layout inspector in Android Studio Electric Eel. Inside this layout inspector, there is a toggle to enable a composition count. So what it does is it shows you a number of recompositions as well as number of skips, which is really good for understanding recomposition in details. And this is a very handy tool, right? Because you don't need to manually add it to each composable functions. You don't need to maintain that modifier function and so on. However, again, Electric Eel is a Canary build, right? Some people might not be happy, might not be comfortable using Canary builds, and they want to wait until the actual official release, which may take a time. And also that recomposition counter is available for Jetpack Compose 1.2 and higher. So if you're using Jetpack Compose 1.1, which is a latest release, you might not be as happy about that. So as you saw in the smart recomposition section, Compose naturally tries to avoid unnecessary work, right? Unnecessary recompositions that will cause to repeat the phases all over again. But to help Compose even further, we developers can use some tips to leverage that smart recomposition. And so the first tip being breaking down your composable functions as much as possible. There are different ways of structuring the composable functions, right? You may decide in this example, for example, you have a column, you have a composable function greeting 1 and greeting 2. You might think first naive approach is to add the another column inside that outer column and add this text with the numbers, right? And plus also introduce another column. So have this sort of a nested column situation. And what happens in this example, whenever the recomposition occurs, like let's say you change the text in Android, it's going to search for the nearest scope and update everything inside the scope, which means you may potentially end up updating the other column that is not necessary to be updated in the first place. Number 2, using key composable. So I've briefly mentioned about different groups that runtime assigns for for some composable functions, right? So on top of assigning a group and with the group key, it also assigns a specific type for groups, like restartable, skippable, replaceable, and movable groups, right? And when the key is not set inside that group, right, runtime cannot determine whether the item inside that group was moved or was it changed exactly. And by setting the key, you're basically telling runtime, about this unique hash code that will get triggered whenever something gets updated inside the, in this example, inside the lazy column, right? For example, here you see how we have 5 items, and we remove that strawberry, I believe, yeah. So we remove the strawberry, and underneath there's blueberry and banana. They do not get recomposed. But if you do not have a key, what happens upon removing that strawberry, banana and blueberry ends up getting recomposed, although the value input has not changed there at all. And number 3rd tip is deferring the state read as at lowest composable function as possible. So by deferring the state read all the way down to the actual consumer child node of the state, runtime will recompose only that function and not the parent or subsequent parent of it, right? Again, it all comes down to that scope issue where you might possibly end up recomposing the outer scope that is not necessary and possibly the other functions that have not been updated inside that scope. So for example, like let's say if we have Android text inside the cart video, and we're also changing the value from like view to Jetpack Compose, right? As we see here, the raw itself with the image and the text, raw itself doesn't get updated. However, good inner column that contains that Android and the Jetpack Compose versus View Compose, only that part gets recomposed, and not the good row. And number 4, using modifier lambdas. So that's another, it's kind of a continuation of the previous tip where I was talking about reading at the lowest possible composable function. And here, when a state value is passed to the modifier function, right, the read happens at that exact specific moment, therefore causing the nearest scope to recompose. And then when state value is passed to the modifier function, to the lambda function, the state read is actually deferred up until the latest phases like layout and drawing, only then happens. For example, here, I'm using the lambda modifier offset, and offset technically responsible for placing a UI component on the screen, which means offset lambda will be called only upon the layout phase and not the composition, like as if I use the regular offset function instead of lambda function. All right, tip number 5, utilizing derived state of. So let's say you have a object that depends on another object that could possibly be frequently updated. For example, in this example, we have a hide bottom bar, right? So whenever you scroll, your bottom bar gets disappeared, and whenever you pause that scroll, your bottom bar appears again. So what we see here, the variable hide bottom bar is dependent on the list state, right? Is scroll in progress. And because scroll in progress is frequently changed state, what we can do, we can derive the reading of the state until the latest moment where exactly the hide bottom bar is used inside the animated visibility. That will help us to recompose as little, to reduce the recomposition of this specific bottom bar. Okay, and the last one, tips worth repeating. Number 1 tip is moving all your logic out of the composable functions to view models, presenters, and so on. You want to keep your composable functions, as little logic as possible, ideally no logic at all. And then try not to create any dependable functions that depend on the result of the other function, right? For example, if you set a global variable in one composable function, then you end up calling that variable inside other composable function what you end up having is you might not get that latest value inside that global variable because Compose tries to optimize as much as possible, which means the execution of these composable functions can happen in parallel. It can also happen in any order. So there is no guarantee that you might get the latest information. And so if you have side effects that depend on the UI being displayed, right? The thing about side effects, they get applied whenever they get applied and updated, even if composition is canceled. And then when recomposition is canceled, Compose discards the entire UI tree from the recomposition count, which will lead to this inconsistent state of having information coming down from the side effect, but you don't have that UI tree in place. So if you need to trigger side effects, try to use callbacks like on-click listener and so on, and try to trigger the side effects inside those callbacks. And so what does recomposition mean to your app? In Jetpack Compose, UI widgets are functions, right? They go through 3 phases: composition, layout, draw. And when they go through these 3 phases, under the hood, the Compose compiler, synchronizes 3 layers: compiler, runtime, and UI, to create and deliver this composition to Android operating system. And whenever the state of the UI widget changes, the recomposition is triggered. Recomposition is a natural and expected process, but sometimes not knowing well the rules around the recomposition will cause your app to have a bad performance, unexpected behaviors, drain battery. And so when you write composable functions in Jetpack Compose, keep in mind to leverage smart recomposition as much as possible and use practical tips of writing good functions that I mentioned earlier. And so this is the list of great resources that I have compiled for this presentation, and wouldn't happen without my colleague Jorge Castillo's book, Jetpack Compose Internals, as well as Chris Payne's article on the Compose compiler metrics, and so on. I've also included the QR code for the recomposition tips, exactly where you can see the bad examples and good examples as well, so you can compare and see. Once you run that repository, you can see like how many times it gets recomposed, like the common mistakes that people make in the beginning. That will help you to learn more about the recomposition. And so, thank you so much, everyone, for coming in and staying in till the last moment. If you guys have questions, do I have time for questions?
We can do a couple minutes.
Couple minutes for questions. Yes.
Yeah, so I noticed, so first of all, that was a great presentation.
Thank you.
So, yeah, you mentioned that, like, so it basically composition, when the inputs are primitives or strings, it can easily do it, but often it's not very clean. Sometimes you submit a list of value objects or something. So for those value objects, does it automatically, I mean, you went over a little bit, but basically there's an immutable annotation that helps the compiler. So do you always have to use that for every data class if you want to help the compiler, or like why does that exist?
So about these annotations, immutable and stable annotations, it is available for us to use, right? So not to trigger recomposition when it's not necessary, right? So it will help us. However, we have to be very cautious about using that recomposition, that stable and immutable annotations, because it means also you might end up in the situation when you're expecting that update to go through and see on your screen, right? You might expect the recomposition to happen. However, it's not happening. Why? Because you have annotated with like @stable or immutable, and when you call this equal, when the runtime calls the equals function, compares the hash code, it just skips that calling that equals function. It does not compare those values, so you might not end up seeing this recomposition. So I guess it comes down to the trade-off of, would you like to see frequent recomposition, or would you like not to see any updates, right? So like it's a trade-off of those like examples. Like it's either this or that, and that's why they provided annotations for you to make more meaningful decision, like, and taking an ownership when you use those annotations. That's why.
So basically, I'm asking if the immutable annotation is necessary. So we have a simple data class speaker with name and right? You only want to change it if name or company changes, right?
Yeah.
So do we need the immutable annotation or not?
Does it come as a UI state? If so, yes. Because like
we do want
yes, I would personally make it as immutable.
If we did make it immutable, would it recompose even if the contents of that object were the same?
Like, let's say if you're using as a unidirectional flow and that UI state that contains a list of names, right, or like list of the custom type comes from the view model, and then your composable functions observe that UI state, what happens is not going to compare. It's just going to spit out a new value to it. So it's going to display that information. So that's what I would explain. Does it make it clear? I think it doesn't make it clear.
Yeah, I think I'm just, yeah. Well, yeah, and if, basically, yeah, I mean, you don't want to trigger recomposition when it's not necessary, but you do when it is necessary. So, yeah, still, yes, I think I can. Maybe we can go over it after.
Sounds good.
Yeah.
Yep. I think it's about like how you're gonna use as a. It's not just thinking about that as a like type of list or anything like that. It's about how you use that, how you wrap inside UI state, and how you call that UI state, and how you pass down to your composable functions. I think that's where the element is missing as well too. So because the consumers, which are your composable functions, technically they're gonna be observing that state, right? And then because you have remember a mutable state of, right, which is contains the information about that, that state will get updated every time with the immutable. So if you put the immutable, yep.
Like, yeah.
Yes. Now I'm thinking. Yeah. Now I got your question.
When to put the immutable? Do we need? Well, I guess when to put the immutable and when not to. Yeah.
That's a good question. I would actually. That's the thing about the annotations. I would be very cautious about using them at all times, because then basically you're telling the runtime, hey, you can skip this recomposition. You don't need to worry, because I am, as a developer, telling you that the content of this list is the same. Like, you don't need to worry. So that's where it gets tricky. I would be very cautious of using these annotations. But if you for sure know that the content doesn't get updated as much, and you guarantee as a developer, you can use it at your own expense. The question, so would you want to have too many recompositions, or would you want to have very little recomposition when it's not needed? If I were to choose, I would go with a more frequent version versus not a version at all, because it helps, like, at least you're going to see the updates on the screen, and then being concerned a little bit about performance would come later, like when you debug more and understand what's happening, stuff like that. Awesome. Thank you.